Hello, my name is Josh Demude, and I will be presenting my research done in collaboration with Andrea Risha and Christian Scheidler on the canonical Amoebot model, algorithms and concurrency control. The Amoebot model is a model of programmable matter, which is a substance that can change its physical properties autonomously based either on a user controlling it or in automatic response to environmental stimuli. Computer science and robotics usually consider programmable matter as a modular robotic system where the individual entities are homogeneous robots, and these robots must communicate and move and cooperate to solve some sort of collective task. Now, the Amoebot model has a 8 or so year history now, and it's useful to be familiar with what it looked like before this paper and to understand how we changed it going forward. So the geometric Amoebot model assumes that space is a triangular lattice, like you see here on the right. And Amoebots are these nodes. They occupy the nodes of the lattice, either as contracted, meaning they occupy a single node, or expanded, meaning they occupy a pair of adjacent nodes. Individual Amoebots are anonymous, so they don't have any unique identifiers. They have constant size memory. They can only communicate with those in their immediate one neighborhood, and they don't have any global compass. They move in an active way, meaning that they decide where they want to move and when, via expansions, which is when a contracted Amoebot stretches out into an adjacent position, followed up by a contraction, where it once again goes to occupy only a single node. Handovers are just a way for neighbors to do expansions and contractions together. And then finally, up till this point, the Amoebot model has primarily considered sequential activations, where only one Amoebot is active at a time, and an adversary is allowed to choose which Amoebot gets to go next, so long as every Amoebot acts infinitely often. So under this formulation of the Amoebot model, there have been about 30 or so papers since this was originally introduced at SPA 2014, looking at a whole variety of problems, ranging from shape formation to leader election, object coding, compression, bridging, convex hull formation, collaborative computation, just all sorts of things. And as this has evolved, so has the model. Different papers have adapted the model for their own needs or tried to extend it to more realistic situations. And so where we are, kind of at present with this present paper, is that the Amoebot model, like many new models, is now lots of models in one. So one issue that we're trying to address here with the canonical version is trying to give a unified language from which to describe all of these different variants. Now, a second issue that we're addressing with the canonical model will become apparent when we compare to related others. So there are other models of programmable matter, those like population protocols, network constructors, and DNA tile-based self-assembly. These are non-spatial models where the entities are passive, meaning they often don't control who they interact with. The Amoebot model is the opposite. So here, Amoebots are under full control of their decisions, and they are spatially situated, so they occupy physical space. Similarly, autonomous mobile robots, and especially those using discrete graph-based models of space, are similar. These mobile robots are also anonymous. They choose their own movements but don't have global orientation. They have limited computing and sensing capabilities, and with some extensions that were introduced along the way, like persistent memory in the F-state model and limited communication in the luminous robots variant, or robots with lights. This gets us very close to the kinds of things that the Amoebot model cares about. Nevertheless, there are a few differences that do matter. First of all, Amoebots respect physical exclusion. This means that at each node, there can be at most one Amoebot, whereas in the mobile robots, many agents can pile up on a single node. This does affect algorithm design, especially when there are conflicts, like multiple Amoebots trying to be in the same space. So this makes the Amoebots a bit more complicated. Secondly, the mobile robots use a well-established look, compute, move cycle to govern their actions. So this means that a mobile robot wakes up it snapshots its neighborhood, it computes what it wants to do based on that snapshot, and then it maybe moves. It depends on the action, but it might move based on what it computes. This is a difficult thing, especially the snapshots are difficult to rectify with traditional message passing. And the Amoebot model also to date has assumed sort of a stronger communication variant where neighbors can access one another's memories, which is not quite the same thing as looking. So there's some work to be done to reconcile those things. And finally, mobile robots have historically used a well-defined, clear hierarchy of adversarial schedulers. So sequential, semi-synchronous, fully synchronous, asynchronous, and as well as a bunch of fairness conditions to decide who gets to go and when, and how to model concurrency. To date, this is something that the Amoebot model has lacked and is yet another thing that the canonical model is trying to fix. So moving on to our results, we're going to do three things in this paper and in this talk. The first is that we will introduce the canonical Amoebot model. It does two key things. The first is that it provides a standardized hierarchy of assumption variants so that it will be easier to compare not only Amoebot algorithms, but also the Amoebot model in general to other models of programmable matter. And number two, it will take all the high-level stuff that the old Amoebot model had and take it down to the level of message passing and movements so that we can study concurrency under adversarial activation models in a meaningful way. The second thing we'll do is start to tackle this concurrency problem. So we'll identify a set of sufficient conditions for an Amoebot algorithm to be correct under a concurrent adversary. And after identifying those sufficient conditions, we will give a hexagon formation algorithm that actually satisfies these conditions. The last thing we'll do is take this problem of concurrency control and tackle it with a general framework. This framework you can think of as a compiler. It's going to take algorithms that terminate under sequential adversaries and satisfy certain conventions, and it will translate them into algorithms that exhibit equivalent behavior, equivalent correctness under asynchronous adversaries. So this takes some of the difficulty out of designing correct asynchronous algorithms. Let's start with the canonical model. So as I mentioned, it first introduces a hierarchy of assumption variants. We won't go through all of them, but you can see there are different assumptions one might make about space, whether it's a lattice or it's just a general undirected graph, what kinds of orientations the Amoebots do or don't share, the amount of memory on board, and then the key focus of today's talk, the adversary's concurrency and the adversary's fairness. So who's allowed to be active at the same time and who is guaranteed to get activated and when. A key difference from previous versions of the Amoebot model is that the canonical model is going to split Amoebot functionality into two layers. So there's a high-level application layer where algorithms are defined, and then there's a low-level system layer. These layers talk to each other through what you could think of as like an API, which we call operations. So these operations, which are listed in the table on the left, are really high level, right? Like, for example, this read operation is just, I'd like to read the value of X on the port P. Or, for example, this expand operation, I'd like to expand towards the direction of port P. All very high level stuff. And when the application layer calls it, then the system layer has to take over and actually do whatever is required there, all in terms of asynchronous message passing. So this diagram on the right is a sort of execution flow for the read operation. You can see that there's a variety of things that the system layer has to check, messages that need to be sent, waiting that has to happen for responses and so on. And a key difference from the past, operations can now fail under certain circumstances. Okay, so we have this kind of thing for all 10 of these. And the last thing I'll say is that there are two new operations, lock and unlock, that are our new concurrency control operations. This encapsulates a version of mutual exclusion where an Amoebot's going to try to gain control over its immediate neighborhood. And I'll say more about that in a bit. Algorithms are now defined in terms of guarded actions. This is similar to the very old way that Dijkstra even defined progress for asynchronous message passing systems. And the way they work is that there's a label, which is just a name for the action. There's a guard, which is a Boolean predicate that determines whether this action can be done or not. If that Boolean predicate is true, we say the action is enabled. And finally, there's a set of operations. So this is a sequence of computation and operations to perform if this action is actually executed. So here's an example from the hexagon formation algorithm that we'll talk about in a moment. Its name is alpha2. It has this Boolean predicate that has to do with the Amoebot's own memory and the memory of its neighbors. And then there's a sequence of connected read and write operations that happen should this action be executed. So let's dive deeper now into the actual levels of concurrency and fairness. So a sequential adversary is only allowed to activate one Amoebot at a time. So here, the Amoebots are on the y-axis, time is advancing on the x-axis, and you can see that per time, at most one Amoebot is doing anything as indicated by these colors. A k-isolated adversary is a little bit stronger in the sense that it is allowed some concurrency, but only between Amoebots that are not within a distance k, where k is some integer. So for example, if we had this situation of neighborhoods on the right and k was 1, then the red Amoebot could be active at the same time as the blue or the green one because they're not neighbors, but not at the same time as the orange and the yellow one because they are. Okay, finally, we have the synchronous and asynchronous adversaries. So here, they're similar in the sense that arbitrary sets of Amoebots can be active at the same time. But of course, like as is classic in the literature, the synchronous adversary has to do so in discrete rounds, whereas the asynchronous adversary does not. This talk will primarily deal with asynchronous and sequential adversaries. Okay, the adversary also has a level of fairness. This is about who it's allowed to activate and when. A strongly fair adversary guarantees that every Amoebot that is enabled infinitely often is activated infinitely often. So this is a very strong sense of fairness and a weak adversary. The second kind of intermediate level is weak fairness. So here an Amoebot needs to be continuously enabled in order to be guaranteed to eventually be activated. And then finally, there's the unfair. So that just means the adversary is allowed to activate whoever, so long as that Amoebot has something to do. This is primarily what we'll be talking about, unfair asynchronous adversaries, meaning that the adversary can activate any Amoebot with something to do whenever it wants to. So that concludes sort of the intro of the canonical model. Let's now move on to asynchronous hexagon formation as a first case study for what this model looks like in action. So this is a classic shape formation problem. It's been studied a lot in the Amoebot model. We're trying to take an arbitrary connected system and have it self-reconfigure so that it forms a regular hexagon or as close to one as possible, given the number of Amoebots. As is normal in this literature, we will assume a unique seed Amoebot already exists, for example, as the result of leader election. Okay, our hexagon formation algorithm is defined here in terms of actions like we require with the canonical model. And it is done so inspired by the original algorithm by Dirac-Shinde et al. In 2015. But here there's a lot of subtlety in getting this to work correctly in terms of actions. When we go to analyze this algorithm, we're able to prove the following theorem. So assuming geometric space, which is the triangular lattice, assorted orientations, which means they don't need to agree on a global compass, and constant size memory, this algorithm is correct under any adversary. Specifically, we're going to prove this for an unfair asynchronous adversary, which is the most general of all. How we prove this is we first show that the algorithm works in the easier sequential setting. So this is kind of the normal way that Amoebot algorithms are analyzed. So we know that sequential things work. Then we show two key properties. One, if an action is enabled, then it will remain enabled despite any concurrency going on in that Amoebot's neighborhood. Number two, if an enabled action is executed, then it will execute successfully and identically in both a sequential and asynchronous setting. So here we have this arbitrary asynchronous thing going on. What we're going to show then with these two properties is that we can serialize that execution. So we can take the concurrent version and provide a sequential ordering of the action executions such that the same outcome is produced. And as long as we can show that all asynchronous executions are finite, then this all goes through and we get unfair asynchronous correctness. Now, as it turns out, these key properties hold for any algorithm, not just for hexagon formation. It's sort of agnostic to the actual algorithm itself. If you can show these three things, namely correctness under an unfair sequential adversary, enabled actions remaining enabled, and enabled actions remaining successful and unaffected by concurrent executions, if these three things are true, then the algorithm is automatically correct under an unfair asynchronous adversary, or any adversary for that matter. And notably, this is true even without using those lock and unlock concurrency control operations that we introduced with the canonical model. So this demonstrates that while locks are useful, they're not always necessary to get concurrent correctness. Okay, so now we turn our attention to the third and final contribution of this paper, which is a general framework for concurrency control. So with hexagon formation and with those sufficient conditions we just talked about on the last slide, we showed how an individual algorithm can be carefully designed so that its actions are ambivalent to the effects of concurrency, but this might be very difficult to achieve in general. Instead, we'd like to use locks in a general way. And what we will be doing is starting with an algorithm that works under an unfair sequential execution, and use locks to lift it so that we get an equivalent algorithm that works under an unfair asynchronous adversary. So we're right here in the middle, and you can think of our framework like a compiler that's taking the inputs on the left and outputting the algorithms on the right. If such a thing could exist, then this is truly the best of both worlds. Moving forward, algorithm designers would get the ease of working in the sequential setting, but would get the advantages and the relevance of having their algorithms work in the real concurrent world. Now, this pipeline is a bit too idealistic in general and may actually be impossible. So we're going to require that the input algorithm satisfy certain conventions before we guarantee that the framework is actually going to work as advertised. So let's start with a set of key ideas that our framework is going to operate with. The first thing that an Amoebot is going to do under the framework is try to lock its neighborhood. Locked neighbors will not move and will not change their memory contents, either by writing to themselves or having neighbors write to them. So because this Amoebot knows that its neighbors won't change, it's going to be able to evaluate its guards and perform its actions almost as if things were sequential. Moreover, because of the careful way that we design this thing, we're going to guarantee that any failures in this, so either in the locking attempt or in an expansion where two Amoebots try to move into the same position at the same time, we're going to do this very carefully so that such failures are not going to have a lasting effect on the rest of the system. So in this sense, this is kind of like an isolation property that we're gaining. Now, this is all wonderful, but there's a key issue. Locks, and for that matter, any other algorithmic mechanism, are not going to be able to stop other Amoebots from expanding into an acting Amoebot's neighborhood. So you think about it, an Amoebot A wakes up, it locks its neighborhood, but then somebody who wasn't in the neighborhood to begin with might come into the neighborhood and start messing with things, and they're unlocked. They're able to do whatever they want. So let's just look at a quick example of how this breaks down, and why, in fact, this is a key issue, not only for our framework, but for any kind of approach that is going to try and address concurrency control. So imagine that we have a very simple algorithm. If I have no neighbors, then expand forward, where forward is going to be marked by these little ticks that the Amoebots have. In the sequential world on the left-hand side, we might activate one Amoebot at a time and see that lo and behold, at their beginning, they don't have any neighbors, so they get to expand. But eventually we'll hit a point where at least one Amoebot will now have a neighbor and will not be able to expand, right? Now, in the asynchronous world instead, they all could get activated at the exact same time and all expand and now form this sort of expanded cycle thing. This is impossible for a sequential execution to reach and is a good counterexample for showing a non-serializable execution, right? There is no sequential ordering of these expansions that would create this cycle because of what we saw on the left. So we need to do something about these expansions that can come in and mess up action executions. So the way we're going to handle this is by setting some conventions. Number one, we're going to require that the algorithm is valid in the sequential setting. This is a given. If it doesn't work in a sequential setting, it's not going to work in the concurrent one. So fair enough. Number two, we're going to require that all compute operations, so those are read, write, sensing, and computation, those all need to come first, preceding at most one movement. And then finally, this is the more technical convention that limits the generality of the model more extremely. We're going to require monotonicity. Monotonicity at a high level is the thing that's going to ensure action executions are not affected by unlocked Amoebots that concurrently enter the acting Amoebot's neighborhood. We'll go through a couple examples quickly. Here, Amoebot A is the one that's acting. These empty locations are unoccupied. And these blue neighbors are the ones it has originally. When it does this action alpha, what it seems to do is just it goes ahead and updates the memory of B. Monotonicity says that if instead it were to have these red neighbors that additionally come in and enter the neighborhood midway, then the only thing that an execution of alpha will do is exactly what it did before, writing to the memory of B. It's not going to affect the new neighbors. It's not going to do something different. It's not going to fail. It must do exactly the same thing. A more complicated example is here on the right. Here, when A goes and does action alpha, it's going to write to the memory of B and pull its neighbor C in a pull handover. Once again, if there are new neighbors, it needs to do exactly that and nothing more, nothing less. A key open question is, okay, that seems to solve a lot of problems, but do there exist any algorithms that satisfy this? And the answer is yes. Static algorithms, or stationary ones that don't involve any movement, are trivially monotonic because monotonic conditions are only worried about when Amoebots are entering the neighborhood. And this is a non-trivial class of algorithms. Most of the leader election algorithms, with the exception of Emick et al.'s iCalc 2019 paper and the more recent one by Shai Kutin et al. At PODC 2021, all the other ones are stationary. How does this work? We'll go through this quickly. First, an Amoebot attempts to lock. I'm sorry. How does this concurrency control framework work? Well, it takes in an algorithm with a bunch of actions and it outputs an algorithm with a single action. And that single action has all of this code here as its operation, which causes the Amoebot to first attempt to lock. Then if it succeeds in locking, it evaluates all the guards of the original algorithm. If it finds that one of those guards is true, then there is an enabled action. It, in private memory, emulates the compute phase. So it doesn't actually do any of this, but it emulates all the connected read and write operations. So it knows what would happen if it were to do it. And if that compute phase contains an expand operation, it goes ahead and attempts to do so. Steps 1 and 4 are the only places where this thing can fail. After that, we're in the point of no return, where it is totally safe to go ahead and change the configuration of the system. So here, it's performing any write operations that it might want to, and then it goes ahead and does other movements. And these are safe because we know that the thing will not fail anymore. There's a little bit of other bookkeeping that happens throughout, but we'll skip over that. So with these 3 conventions in place of validity, computing before moving, and monotonicity, we are able to prove the following theorem. If you have an algorithm A satisfying conventions 1 through 3, and A prime is the algorithm that the framework gives you, Then, so long as A terminates under any sequential execution, every asynchronous execution of A prime terminates in an outcome that some sequential execution of A could also have terminated in. That means that we get this pipeline. We started with an algorithm A. If it satisfied these conventions, then we get this new algorithm A prime, and these do end up in the exact same outcomes. So we know that sequential correctness gives us asynchronous correctness. All right, so we'll conclude with some open questions. First off, we now have a new model, right? The canonical Amoebot model, and a whole bunch of existing algorithms. So if we were to standardize these existing algorithms according to the hierarchy of assumptions and the action semantics, we can now ask more meaningful questions about how these algorithms compare to one another. In particular, with problems like leader election, where there are many papers coming out that are each claiming to be better than the last in different ways, this kind of comparison within the hierarchy will be very useful for understanding how comparisons actually work. Number two, the canonical model should be extended to address fault tolerance, but the question is how. To date, crash faults have only been considered in the Amoebot model for two specific problems, and the canonical model seems to be an ideal structure under which the community should come around and debate a stable family of fault assumptions. Number three, I mentioned that stationary algorithms trivially satisfy monotonicity, but many algorithms for interesting behaviors require movement. So can we show that any of these things satisfy monotonicity and are thus compatible with our framework? Number four, is our framework strictly necessary? That is, does there exist an algorithm that is not correct under an asynchronous adversary without our framework, but is compatible with our framework and therefore gains asynchronous correctness? This is yet to be identified. And finally, as a big question about concurrency control, are there other less restrictive sufficient conditions for asynchronous correctness? This paper and talk have discussed two complementary set of sufficient conditions. The first we showed with hexagon formation was about being ambivalent to concurrent executions around you. The second was the set of conventions that gives you compatibility with the concurrency control framework. These are two complementary different pathways, which provide lots of opportunities for algorithm developers to push this forward. But additionally, it would be interesting to try and identify less restrictive sufficient conditions. With that, thank you very much for your attention. And I look forward to hearing your questions live at DISC.